So the search lemma, so let's start search lemma. So it says that, so consider you have a group operator T, and the group operator T acts on some vector space V. So for example, we already discussed that there is Y, which you get when you act T on X. And then we learned about how to use the basis of the vector space to form a matrix representation of the group operator T. Then we said that if your group operator T looks complicated, then you can always find some matrix such that if you do this similarity transformation, then you will reach a very simple representation of the same group. Oh, sorry. Simple representation of the same group operator T. Maybe by simple I mean maybe some reducible form or something like that. So okay, so this is what we have understood till now. What I will do is we will explore this thing in a more clearer way. So we will understand the similarity transformation in a more proper way. Okay. Okay. Now not only you have to keep the similarity transformation in mind, but you also need to keep one more thing in mind that you studied about reducible and irreducible representation. So if D of T, the representation for group of operator T, turns out to be reducible, then you can always find a representation of T in a different basis, such that if it is completely reducible, maybe you will find reducible representations in this way. Okay, we already discussed this in the last part of lectures. So then this is completely reducible. Okay, so my point is the following. The point is that if you have, say, basis, so let the basis be basis of functions. Okay, we are again going to what we did. Remember we did a problem yesterday where I told you that if you have a certain coordinate transformation and this is your basis and this is the operator, and you found a matrix representation of the operator. We did a problem. So we are going to stick to the basis of functions. So again, consider you have a basis, okay, psi nu, and let me keep it in this way, where nu goes from 1 dot 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 n, and remember always n is bigger than m. So if d prime of T is n cross n matrix, then the reducible or the reduced matrix here is m cross m matrix. Okay, so I took a basis, it has n elements. Now if there are n elements in the basis set, then of course if using this basis I form a matrix representation of the group operator T, my matrix representation will be n cross n. So for example, I hope you understand, it will be an n cross n, right? So consider d prime of T is is represented using n basis set, because of which this is going to be a n cross n matrix. Now this you learned that it is always possible if you say that the representation of reducible. So I'm using the very important thing, if the representation is reducible, so this is the condition, then you can always find another representation. So this is d prime and d prime is n cross n. You can always find another representation which is m dimensional representation of T. Okay, so which is like m cross m matrix. Okay, that means that for the same operator you can find a set of bases. So let me call this phi L, such that L goes from 1 dot 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 M. That means you can always find a basis set in which you have represented your dm of T. So the small matrix M cross M, which forms a part of bigger matrix, this one, N cross N. Okay, any doubts here? No. So let me move on. So I can write by using the above arguments. Let me change the color. So by using the above argument, I can write that operator O of R acting on the functions, basis functions, will give me some result which can be written and these are the coefficients. And okay, let me use T. I'm not going to use R. Okay, so I'll always use T. So this is what we already know, how to form matrix representation of an operator if the basis is given. And here both the mu and the nu both goes from 1 to m. So nu and mu both goes from 1 to n. Now let me put a prime here, because the prime here means this prime. Okay, so let me put a prime here. And okay, can I change notations for some time? What I do is let me not use the prime here, but instead of prime, why don't I write n here? That will be better. Instead of prime, let me write n. So to tell you the dimension of this matrix, so it will be n cross n. And then if you say that dn mu nu is reducible, that means you can always find another set of bases in which you can represent this. So that means I'm saying that the same operator will have another representation in some lower dimension m of T. That means if I act this on the basis this one, then I can always express them in this way. KL. Okay, so where the L is going from, the L is going from 1 to dot 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 m, and always remember m is less than n. That means the dm matrix is a lower is in lower dimension, and the n matrix is in higher dimension. By lower and higher, I mean you understand, like one is n cross n, which is a big matrix, and another is m cross m, which is smaller matrix, which can be contained inside the bigger matrix after similarity transformations done. So if this is possible, again, if this is possible, that means I can always express the smaller basis set L as a linear combination of the larger basis set, and let the coefficient be alpha rho L. Did you understand this part? That why I was able to write the smaller basis set, because in terms of the larger basis set. Because you see, when you have a bigger vector space and you say that the bigger vector space has two subspaces, V1 and then another subspace V2, then say the basis psi of nu is the basis when you were here, and the basis phi of L is when phi of L is when you are in one of the subspaces. That means that phi of L is not only a basis set, but it is also a vector in V1. That implies phi of L is also a vector in the big V. And hence I can write phi of L as a linear combination of the basis set psi of rho. And can you tell me where rho is going from where to where? Rho is going from 1 to n, and L here is going from 1 to m. So if m and n are different, then you will get a rectangular matrix. If n and m are same, then you'll get a square matrix. We will come to this part later on. Okay, so let me write everything in a new page and explain it in a better way. So what I'm trying to say is that you have, okay, did I just write everything as R? No, so I'm writing T, right? Yeah, so let's continue with our group operator T. So we learned that if you have an operator, the basis psi of nu, it can have a matrix representation. If you do this, what we already learned. Then I said that if the representation is reducible, then you can always find another set of bases, which can also be written as in this way. And then I also said that hence the new basis set, each elements of the new basis set can be written as a linear combination of the old basis set. So I'm saying that if you have an operator OT, then you can always find a matrix representation in a higher dimension. If this matrix representation is reducible, you can always find a smaller set of basis set where you can form the representation such that the smaller form of the basis set is related to the larger set in this way, because everybody is a vector. When I say big and small, okay, let me give you two examples. One example is, consider you are in the same vector space V, and then consider if m is equals to n, then you are in the same vector space V. Okay, that means when you go from the basis set psi of nu to psi of L, phi of L, it means you are in the same vector space and you're going from one basis set to another basis set, and hence you can talk about similarity transformation here directly. Okay, then you can say that the vector dn t, sorry, that representation of group operator T, which is dn of T, is somehow related to the representation d. Why am I writing m? And I don't need to write n or m because we know that they are same. So I just let me put prime. So prime means the matrix representation in one basis, and d of t is matrix representation in another basis, and we know that they must be somehow connected through a similarity transformation. If m is equals to n, everything is simple. We are actually talking about similarity transformation if m is equals to n. But if m is not equals to n, that means we are talking about two different vector space. One vector space whose basis is psi of nu set, where the nu goes from 1 to n, and another vector space, it's using very bad notation. So another vector space U such that the basis sets are phi of L, and L goes from 1 to m, and m is less than n. So you are going to a smaller vector space. So that means the representation at the top of the matrix operator in V, and there is a representation of the matrix in U. So in case 1 here, I can write a similarity transformation in this way. I can always say that there is a matrix A such that if I do this, and if I do this, and if I do this, I get this. Can I write it or not? I can write it. But here, can I say that a representation, so there is a matrix such that the representation in, say, some higher dimension, oh sorry, this is T, okay. So if I write R, forgive me, it's always T. The representation in higher dimension, and this is going to give me a representation representation in lower dimension is somehow related to a representation in higher dimension. Is it possible? I'm asking you, in this case, is it possible? Bikram already discussed do similarity transformation if we are in different dimension. Remember, Bikram? That means if we end up in a case where m is not equals to n, then of course a must be 0. Okay, so what Schur's lemma did is, whatever thing we are going to derive, it will automatically contain these two cases inside it inbuilt. So both these cases are tangled up in the same derivation. Okay, so so again, let me remind you what we are doing. We are going to use these things. We are going to use these things, and I want to show you that these things are possible. In one case, if the vector spaces are same, basis set are in same dimension, a similarity transformation can be found out. If you are in different dimension, then there is no similarity transformation. That means A must be 0. Okay. Now, how are we going to do the derivation? That's important. Okay, and again I say the same derivation contains both the ideas in one form. Okay. Just a minute. Okay, let's see. Let's do the derivation first, and then we will discuss the various cases. So first, remember the three derivations. I want you to remember this three equations at the top, and using this we are going to do the derivation. Just remember these equations. Okay, so when I write phi O of t acting on psi nu, there is a matrix Dn, and here there is a matrix Dm, and here we have alpha rho L. Okay, I need to remember this for myself, and let us start the derivations. Okay, how do we start? So consider that the operator is acting on phi of L. So if the operator is acting on phi of L, but phi of L can be written as a linear combination of another basis set. So the operator stays here, and remember phi of L can be written as rho psi rho alpha rho. But the derivation is very simple. So let the operator act on Vikram, mute. Okay, so how we can start the derivation is, let the operator act on phi of L, which is a basis, but we know that phi of L can be written as a linear combination of the old basis, and the operator OT stays here. And again, I can write it in this way. When O of t acts on this, we know what we are going to get. So there is summation rho, and then there is summation sigma, and we are going to get a psi sigma dn sigma rho of t. So let me keep it here, and then put alpha rho L here. Okay, so what was that? So remember the first relation, O of t acting on psi of nu can be written in this way. So I just used this relation. Okay. Then this thing can be written in a very simple way as summation rho comma sigma psi sigma. So I'm writing the same stuff, just I'm removing the summation. This is what you get. It's very simple. Then what the next step is, what do you see? You see alpha rho L and you see okay. Keep it here. And now remember that you started with what? You started with O of R acting on phi of L. So that means you can now expand O of R acting on phi of L by using the second relation. Let's see what happens. So remember the second relation. So O of T acting on phi of L gives you this. So let's write this one. So O of T acting on this, and you get what? You get summation K phi K D M K L of T. So remember the M or N that I have written at the top is not any indices that runs, but it's just a symbol that tells you in which dimension you are. Okay, that's it. Now this is equal to, if you look at this, then this I can write it as summation sigma K, because I just expanded O of K here. Sigma K becomes psi sigma, so I put a comma here, psi sigma, then D no just a minute. So you have this from the top, you have this from the bottom, and then you have okay. So phi of K can be written in terms of psi, because from the third relation. So let us write it in this way. So the third relation, the matrix was alpha. No, so I should write alpha sigma K and D M K L T. That's it. Now what we are going to do, so we have used all the three equations at the top one by one, and now we know that everything is equal. So somehow this is equal to this. Okay, this is equal to this. So now we are going to equate these two stuff, which is quite natural. So let's equate them in the next page. So we found that summation sigma rho psi of sigma D, I think there was N sigma rho, and this is matrix representation of T, not to forget, alpha rho L is equal to sigma K psi sigma alpha sigma K D of M K L on T. So quick check. dm here, dn there, and this is what we get. Let's see. Yeah, this is what we get. You can remove the summation signs if you are familiar with Einstein summation convention. You can remove the summation signs. If not, you can keep the summation signs. Okay, both sides we have this LHS part is equal to RHS part, but there is an interesting thing is the psi of sigma, both sides are linearly independent, right? The idea that psi of sigma, where sigma runs from 1 to n, it is a basis. It means that each vector is linearly independent. So if psi sigma on both LHS and RHS are linearly independent, that means the coefficients here can be equated in the following way. So I get summation rho d n sigma rho of t alpha rho L is equal to summation k alpha sigma k d m k L of t. Now this whole thing that looks complicated, but it is nothing but its matrix multiplication d of t multiplied by some matrix A. This matrix is related to these coefficients is equals to A d prime d n and d m of, that's it. So from here you can do one more stuff, but we will not do right now. You will say that, hey, can I do this? Can I do this? I'll say not right now, not right now, because you don't know if A is invertible. We don't know that. Okay, so let's give a space to that and keep the whole derivation up to here, and then we start discussing various cases. So case number one says that if your m is equal to n, which is very simple case that you already know. So if m is equal to n and the above equation is true, okay, then we say that A exists and A is invertible. That means dn, so both the d's, they are equivalent to each other through a similarity transformation.
Excuse me.
Mm-hmm.
In this case, how did you understand A is inversible?
A is invertible because you are in the same dimension, right?
Mm-hmm.
If you're in the same dimension, you can always find the matrix A such that you can go from one representation to another representation, because the matrix A is closely related to change of basis.
Mm-hmm.
Remember, and we already did that in the previous classes.
Yes.
Okay? But if m is not equals to n, then what will happen? Then it will happen that A must be 0. Okay? That means if both the d's, dn and dm, if they are two irreducible representation of group G, what did I say? I say if they are irreducible representation of group G having different dimension, then A has to be 0. So again, if dn and dm are, look at the word, irreducible, or irreducible representation of group operator T, then for m not equals to n, A has to be 0. Else you cannot satisfy all the conditions at once. You cannot have m not equals to n and A not equals to 0.
But when
okay?
we started,
Now if
when we started, dn was a part of the n.
Yes, yes. So we started in that assumption, and there are two cases. M can be equal to n. If m becomes equal to n, then both the bases have same dimension. That means both should belong to the same vector space, and the matrix A takes you from one basis set to another basis set if M is equals to N. But to generalize the notion of similarity transformation, we took let M not equals to N, because if M is not equals to N, then I can say that, hey, look, you have a representation of in a basis set with M basis, and you have the same representation of the group operator in the basis set with N basis. If it happens, so one representation is in higher dimension and one representation is in the lower dimension, then you can say that, okay, can I find a similarity transformation of the higher dimensional complicated representation such that when I reduce it, then when I reduce it, then the matrix will have the lower dimensional representation sitting in one corner. Yes?
Okay.
Okay?
Okay.
So this is the whole idea. Then what is that? It is said that if both the dn and dm, okay, so if both dn and dm are irreducible representation of group G having same dimension, that means I'm talking about M equals to N, then there are two possibilities. One possibility is yes, A exists. In that case, dn and dm are equivalent. Another possibility is maybe A will be 0. Okay, two possibilities exist when M is equals to N. So either A exists or A equals to 0. But when M is not equals to N, then there is a problem. You cannot have A exist. Okay, and there is one more case. Now if you look at this T, we talked T as a single group operator. What if I talk T in when I talk of T, I talk about all the group operators. That means if I say that, hey, look, you can have this relation dn of T, some matrix A is equals to A, some matrix M of T. So you have this relation, and this relation is true for all the operators T that exist in group G. Imagine that this relation is true for all the operators of a particular group. Then the only outcome that you will find that A is equal to constant and is equivalent to an identity matrix. In other words, if a matrix commutes with the matrices of all irreducible representation, the matrix must be a multiple of unit matrix. So let me put a lambda here. When I write this, see, this is very interesting. When I am writing this relation, not just for one group operator, but I'm saying that it is true for all the group operators. I am making a bigger statement. If I'm saying that this is true for all group operators, then what is the status of A? Status of A is a matrix that commutes with all the matrices of an irreducible representation. Look at how big the status of A becomes. So if the status of A becomes that big, then it turns out that A must be some multiple of unit matrix, else this is not possible. You cannot have any matrix A that commutes with all the irreducible representation of the group element. So this is, you can say, case 3 when I'm talking about all the group elements. What I want you is, I want you to contemplate on this. Okay. That is what is needed. Else you will not understand. I want you to contemplate on this for a certain time. So let's end the class here, and maybe we will do the class after 20 minutes again. But I want you to, I will send you the PDF. I want you to think on this. Okay, else you will not